Okay. So basically what we want to do, okay, we would like to find the transfer function from V3 to V1 by utilizing, okay, the signal flow graph. Okay. In order to use the signal flow graph, let me construct the signal flow graph for this circuit. And we have said variable R, V1, I1, V2, I2, and V3. Those are my variables. Okay. So let me establish what are the relationship between them. Okay. What are the relationship between them? Okay. First of all, what is I1? I1 in terms of V1 and V2. What's I1 equal to? Any help?
We take KPL.
Okay. Or
I1 is V1 minus V2 over R1.
exactly. 1 over R1, V1 minus V2. This is I1. How about V2? V1 is my input. It's given to me. Okay. So what is V2? Based on the variable which
1 over R2.
no
I1 minus I2 over R3.
multiply يا شيخ multiply
multiply.
overflow. والله في مقابله يودوك بداهيه يا ابني. I1 minus I2. Okay, now I need I2. What's I2 equal to?
V2 minus V3 over R2. V2 minus V3 over R2.
V2 minus V3. Finally, V3. What's V3 equal to?
R4.
Uh-huh.
I2 minus I3.
What's I3?
I2 only.
I2 minus I3.
What's I3?
I4.
What's I4?
Plus V2.
Only I2 يا ابني. There is nothing. This is open circuit. So I in here equal to 0. So it's just I2. Okay. Now, the objective is to relate V3 to V1 and eliminate anything in between. We are going to do it through, you know, as I said, Mason's rule and signal flow graph. Now, let me convert those equations to construct my signal flow graph. So what's I1? If I want to have the signal flow graph, what do I have? What's I1 will be? What do I put in here?
Multiply by 1 over R.
Okay, so it's going to be 1 over R1. Okay, this is what we call the node, but we call it a source node. In this node, I don't have anything coming to that node, but things are going out. Okay, so 1 over and minus 1 over R1. Do you agree? This is, I'm converting this equation and I'm putting it in here, in this node. Now tell me what is V2?
Victor, where do we put the sign?
Why do I get what?
Where do we put the sign of V2?
Oh, sorry. This is minus.
Okay.
Associated with the gain. Okay, how about V2?
Multiply by R3.
I1 and R3, and
minus I2.
Minus, okay, minus R3. I2 1 over R2 and minus,
1 over R2.
what about V3?
R4, I2.
R4. And this is my signal flow graph. Is the signal flow graph clear? Once you have the signal flow graph, now it is very easy to find the relation between V3 and V1. How do I proceed? How do I proceed?
Find the forward path.
Exactly. Okay, tell me the forward path. For P is the forward path, let's say.
1 over R1
Okay,
multiply R3
R.
multiply R3 1 over R2 multiplied by R4.
Exactly. This is the path. And I have only one path. How many loops I have?
3 loops.
3 loops. L1 will be, what's the gain of L1?
Minus R3 plus R3 over R1.
Which is the negative because this is the minus in here. Okay. L2
Minus R3 over R2.
and finally L3 will be
R4 over R2 minus R4 over
minus
R2.
R4 over R2, sorry. And there is the minus sign.
Doctor,
Yes.
when we write the path, we don't consider I1 and V2.
No, we consider them. Those are the variable. But if you remember, in the path, we take the gains only. We multiply the gains. We don't multiply the variable. We take the gain associated with those paths.
Okay.
Only the gain. Okay. Now, I want, okay. Do we have any non-touching loop in here? Any non-touching?
L1 and L3.
L1 and L3, they are non-touching. So basically I will have L1 and L3 equal non-touching. Okay. And the gain is going to be, okay, it's going to be definitely L1 we said R3 over R1 times, and there is minus sign, and the other will have minus sign R4 over R2. Now I need delta. What's delta equal to?
1 minus single loops, the summation of single loop, plus the 2 untouching loop summation.
Great, thank you. How about the cofactor, delta 1, cofactor of the path 1, of the path, which I have?
0. 1 minus 0 will be.
So it's going to be, it's not 0,
1.
1. Because we take out all the loops which are, you know, touching the path. And since all the loops are touching the path, so I will have delta 1 equal to delta. Delta 1 equal to 1. And my transfer function is going to be simply this. After simplification. Any question, Shabab? Any question? Okay. If there is no question, we can proceed. So let me stop sharing in this one and let me share it. No, this one. Stop sharing. Okay. Now we would like to move into a new topic. Let me put this course roadmap again to remind you where are we and what did we do and where are we going. So far, if you remember, we did the modeling for the modeling of electrical system, which is basically circuits, electromechanical system, DC motor and generator, and simple, mass spring. And what we came up with, the differential equation model. Okay, so the first thing, if you have a system, how do you get the differential equation model for that system? How do you get the differential equation model for the system? What did we do?
We use Laplace transform.
What?
We use the Laplace transform and block diagram.
No. The differential equation model. So the first model, differential equation. If you have a system, okay, how do I obtain the differential equation for the system? Circuit, for example. What do we do? If I have, let's say, I have 2 capacitors and 4 inductors, okay, and I want to get the differential equation model, what do I do?
We use the relationship.
Yeah, through what? How? What did we do? We said,
For example, we use machine. We use the nodal analysis or the mesh analysis
exactly
for the circuits, and for other systems like the mechanical system, we use the Newton's law, second Newton law with the So we have certain laws, we apply them.
Okay, now in the differential equation, what will be the model of what will be the order of the differential equation? It depends on how many energy storage element we have. For example, when I said suppose I have 2 capacitor and 3 inductors, what will be the order of the system? What the differential order model is going to be?
It's going to be 4.
No, if 3 and 2, I said 2 capacitor and 3 inductor, or the other way around. Okay, 1 by 1. Okay, 1 capacitor, 1 inductor. What do you think the differential equation is going to be? What's the order of the differential equation is going to be?
Second order.
Second order. If I have more elements like capacitor, inductor, I will have higher order differential equation. And this is, as Abdurrahman said, we will apply KVL, KCL, or Newton's law to get the differential equation. Then we also study the transfer function model. And how do we get the transfer function model?
Doctor, here's a question. Usually in a real system, we have, I would say, infinite number of storage elements. So our system will be very huge if we use the differential equations. Therefore,
first of all, realistically speaking, there is no infinite. We will be.
It's very large. It will be, for example, to the degree 40 or something.
Okay, fine. Alhamdulillah, أنت في عصر الكمبيوترز. يعني الحمد لله انت ما اجيت بالاربعينات ولا بالثلاثينات كان او بالسبعينات حتى let's say. At that time, people will not use that higher order because there is no computer. You cannot do now with the computer and supercomputers. It doesn't matter. You just program. Maybe it will take, I remember we were working in, a project. The project basically, the KFUPM has done the study for the interconnection of the Gulf state in one grid. Now, remember the Gulf state are connected electrically. KFUPM has done that study. And, the system is extremely large. And we used to do the run, okay, to do the simulation by special, software. And believe me, it will take 8 hours to do the calculation. That's, that was in the late 80s, okay? Now we have supercomputer and we'll handle more. Yeah, definitely. I mean, the system order depend on how many energy storage element you have in your system, and the more you have, the higher. But even if you go to transfer function, the order is going to be the same. But in the transfer function model, what's the transfer function model? How do we do it? How do we find it? Suppose I have differential equation model.
Taking Laplace.
Yes. So what do we do? So if I have a differential equation model, how do I get the transfer function?
Find the Laplace transform.
Okay. So basically what you'll do, you take the Laplace transform of the differential equation, and what do you do to the initial condition?
Assume it
If
Assume
it
it's
is
zero.
specified as 0, make it 0.
Set it to 0 and get the ratio of the output to the input. So if I have differential equation, I can find the transfer function model. Okay. Now, suppose I have transfer function model. Can I get differential equation back?
Yes, using inverse Laplace transform.
Using what?
Inverse Laplace transform.
Not quite. Look, the way we do it, okay, suppose I have this transfer function. Suppose, let me have a second order system. Suppose I have y of s over u of s equal to, let's say, s plus 1 over s squared plus 3s plus 2. Okay? Suppose this is my, so transfer function is s plus 1 over s squared plus 3s plus 2. Let me make it 3, so there will no zero cancellation. Now, I want to convert this one into differential equation. So what do I do? First of all, cross multiply. So what do you get? You will get s squared y of s plus 3 sy of s plus 3y of s equal to s u of s plus u of s. Remember, s correspond to what in the time domain?
differentiation.
What?
Differentiation.
Exactly. Derivative. dy dt. So if I have second, what do I get? You will have, okay, so you will have the second, let's say, y dt squared plus 3 dy dt plus 3y of t equal to du dt plus u of t. So basically, if you have the transfer function model, you can go back by, replacing each s by a derivative. Okay, look, this is second order. Now get the transfer function. What do you do? Take the Laplace transform or the equation which I give you. It will give you the same. So you can go back and forth. That's basically each derivative represent an operator s. Is this clear?
Yes.
So basically what I'm trying to say, now we took the differential equation and the transfer function model, both of them. Of course, transfer function, either if you have differential equation, you can get it, but you can also get it from the circuit directly. And we have done it. Now, we would like to study a third model called state variable. Let me put it in here. The state space model. What is this state space model? Simply, rather than working with nth order differential equation, I will work with n first order differential equation. That's basically I will have x dot equal ax plus bu, y equal to cx plus du. This is my model. In this model in here, this is a matrix, but I have, let's say, if I have a second order system, I will have x1 dot and x2 dots. So I will convert the, rather than working with nth order differential equation, we will be working with n first order differential equation. So the question is, if I have one capacitor and one inductor, we said the differential equation model will be what? Second order differential equation model, isn't it? Shabab, I have a circuit where I have one inductor and one capacitor. What will be the order of differential equation for that system?
Second order.
Second order.
Differential equation. What I'm saying in here, I'm going to give two first order differential equation rather than the second order differential equation. I will have two, but both of them of first order. This is what, you know, it is differential equation again, but it is of first order. This is,
Any order reduction?
no, it is not order. Look, in the nth order differential equation, you have one differential equation. Now I have n over them. It is not.
Yeah, I mean.
No, it is different representation. It is not reduction.
Yes, yes. We went from second order to first order. So strictly speaking, you are right, Doctor. Strictly speaking, but what I mean by that is that we are now dealing with first order instead of dealing with second order.
So dealing with first order equation, but again, as I said, the system order will remain the same. You need two differential equation to represent the inductor and capacitor. This is basically what we are going to study, and we are going to show that those models are related. If I have differential equation, I can get the state space. If I have transfer function, I can get state space. Or when I have state space, I can get, you know, the differential equation or the transfer function. So our goal in this lecture is to introduce a third model in this course. Okay? Any question before we proceed? The question is, why I bother? Why should I, you know, study the system? What advantage I will have? If the transfer functions model is fine, is nice one, why should I go to other model? First of all, as I said, the model x dot equal ax plus bu, this is, you will be dealing with matrices. And MATLAB is well defined for matrices. This is one. It will handle multiple input, multiple output. Of course, you can say the transfer function will handle multiple input, multiple output. Provide more information about the system. This is new. Now, when you have a differential equation model and you want to get the transfer function, what do you do? what do you do with the initial condition?
0. Set them 0.
You set them to 0. But if you have initial condition, so what do you do? If system has an initial condition and I get the output.
So you have to acknowledge them, and it will be hard for you to use only the differential.
No. Look. Transfer function model is defined for 0 initial condition. So it will not handle any initial condition. While this model, that's basically, suppose I have two system. This has transfer function, let's say 1 over s minus 1, and this is s minus 1 over s plus 2. Okay, and I need, this is u, and this is y, let's say. This is r, sorry, and this is y. Now, if I have this step input, I can get y. But what will happen if I have initial condition in the system? I cannot handle it. While this system in here, look, this is differential equation. So to solve any differential equation, you need the input and you need the initial condition as well. This is one thing. So this model will handle the initial condition.
Especially, Doctor, the point which is MATLAB does all computations as matrix math. This is a very important point when we solve a higher order system, because solving first order will just take the inverse of the matrix. If it's a sparse matrix, it will be easy to process, basically, even.
Well, look, MATLAB now, I mean, maybe when they started MATLAB, it was, only handling, matrices very well. But now, MATLAB becoming very sophisticated. Very sophisticated, even transfer function. Now you can have transfer function. This is, I mean, one thing. But what's important is the other in here. Tell me in here, what will be the transfer function of the system? What is y to r? Can you tell me? What will
1
be?
over, we multiply the two gains.
And what do you get ultimately?
1 over s plus 2.
1 over s plus 2. Now, is this system stable or unstable?
Is stable.
It's stable. Okay.
Because the real part is negative.
Exactly.
There is a cancellation.
Because of the cancellation. Now, suppose you go to the lab, try to build a system, simulate this system. The system from input-output point of view is stable. But if you work in the lab, you will see after a certain time, your system either saturate or it will burn. If this is in a black box, you don't know what happened. While in here, if you use state space, now to start with, okay, what order of the system, what's the order of the system supposed to be?
Second order.
Second order. But because of pole zero cancellation, you see
it appears as a first order, yeah.
First order, and you don't see the, from, I mean, stability point of view, input output stability, the system is fine. This is
a very important point, yes.
Okay, but if you will write the differential equation or the state space representation for the system, okay, which is second order again, x1, x2, okay, you will see that the eigenvalue of this matrix is going to be, one of them is going to be positive, one of them is negative, which means that the system is going to be unstable. This information, okay, is available in the state variables, okay? So the state variables will give you more information about your system. While, okay, it doesn't mean that we're not using transfer function. Transfer function model is much simpler For example, if I have those two, the transfer function is just multiplication of the two. But if I have state space representation and I want to represent the system, it becomes a little bit messier. But it gives me, as I said, it gives me more information about the system. So basically, the state space representation will give more information about the system. Unfortunately, in this course, we will do the modeling of it. We don't go to the design. For example, if I have a system and it's given a state space representation, if it's unstable, how do I stabilize it? We are not going to go to that. There is a concept at the beginning of the semester, I mentioned it, it's controllability and observability. This will come, this is associated with the state space representation. Again, due to the time, we will not, go to that one. So what we will be doing in the coming few lectures is to do the modeling of the system using state space. Any question?
Yes, Doctor. Why we call it a state space? Is there, for example, differential equations, we know that these equations represent the difference and transfer function. We know that this function is transferred the input to the output, or this is the factor of multiplying the input, so we get the output. So from where we can understand or conceive the name of a state space?
Now let's come to the definition of state space. It will answer your concern. State variable model. We call this model similar to what we have called transfer function, the ratio between input and output. Now we introduce state variable. And as I said, the representation of this system is going to be x dot, equal to ax plus bu. This is the state. This is the differential equation part. And then I will have also the output, which is y equals cx plus du. So back to your question, how do I define the state? The state of a system is a set of variables such that the knowledge of these variables and the input will provide the future state and the output of the system. So it is the status of the system. At this moment, what is the status of the system? And what will be the status of the system a little bit later? It came from, maybe from that terminology. So the state variable, which is very important, look. In here, in the state variable, what I need the input, and I need the state. The state, okay. What do we mean by the state? What you need the initial condition. In order for me to find the solution, for example, for differential equation, what do you need to solve any differential equation? What do you need to solve any differential equation?
The initial conditions.
And the input.
Of course.
The force function and the input. So for each initial condition, okay, look, suppose I have, x dot equal, let's say, minus 5x, okay? Suppose I have, I don't have any inputs. What will be the solution for this differential equation?
E to the power minus
x of t equal to what? C
minus 5t.
But C. If you don't give me the initial condition, I will have many solutions. Isn't it?
Right.
So that's why in here, what we are saying, the state is basically what is the initial state of the system. The initial state of the system with the input uniquely determine certain outputs. If you change the initial condition, you'll get another output. That's why, okay, what we are saying in here, the knowledge of these variables and the inputs, okay, will uniquely define the outputs. So if I have a system, suppose I have a system with 2 inputs, 2 outputs, and the system is of nth order. So consider, as I said, consider this system a set of state variable x1 to xn for the system shown is a set such that the knowledge of the initial value of the state variable at an initial time and the input signals suffice to determine the future of the value uniquely. Okay, so the concept of the state, it's come from the concept of initially what do you have, what is the status of the system. Okay, Abdurrahman, I don't know, I hope that will help.
Yes, now it's very clear, Doctor. Yeah, now I have a sense and a meaning of state space.
Now, okay, let's take an example, okay, from circuit, which will hopefully enhance our knowledge. Before that, okay, let me summarize it. I have a dynamic system, I have an input, and I have initial condition, and I'll get an output. Okay, so this is basically the output will be determined by both the input and the initial condition. In the transfer function model, the initial condition was set to be 0. Okay, now suppose I have this circuit and I would like to obtain the state space model that I would like to obtain a system of this format: x dot equal ax plus bu, y equals cx plus du, where x, okay, x dot, I have, let's say whatever number of, x dot represent, many variables, all of them of first order. Now, if I want to write this, okay, if I want to write the differential equation for this system, what will be the order of the system?
This is second order.
Second order. So what I want to do in here, rather than writing second order system, I would like to write 2 first order systems.
Here, Doctor, we have 1 degree of freedom, صح? The system.
We will have 2 degrees of freedom. In the transfer.
Yeah, and yes, and first on, because we have 2. The idea, Doctor, here, if we have only one differential equation in the higher order, so that means we have only 1 degree freedom, right?
In a way, yes. In a way.
Yeah. And for example, the coupled oscillators that we have started with.
You are right. If you want to go to, the design, unfortunately, as I said, we don't go, if you go, inshallah, if you proceed to the master program, there is a call course EE380 linear system. It has only, the only thing which is in there, it is the state space representation. They have transfer function, but the focus will be more on state space. And it shows you the number of degree freedom fallon if you want to do a design. So now, look, if I have a passive circuit, the number of independent variable will be the number of energy storage elements. In here I have L, the inductor will store energy, C will store energy. So my system is going to be of second order. If I have third, let's say another inductor, another inductor, then my system will be third order, and so on. So now let me derive this one. Let me use, for example, this is KCL at this node. KCL in here. What's KCL at this node?
Yes. U of t equal to
Okay. Equal to what? What will be the current?
C dv by dt.
dv c dt plus.
And there y 1 over L, the integration of.
No, wait. Plus IL. This
Yes.
is current. IL. This is the current moving in this direction.
Yes.
Equal to U of t. So let me rewrite it a little bit differently. Let me solve for it, because I need to, I want it in this form. I want the differential equation one side, the derivative one side, and the rest in the other side. So this is going to be dv c dt equal to minus 1 over c IL plus 1 over c u. So this is one differential equation, first order differential equation. How many more differential equation I need?
Another one.
Another
one.
How do I get the other one?
You take it from the maybe KVL.
KVL in the second mesh in here.
Yes.
So KVL in here is going to be what? L. What is the voltage in here?
The voltage here will be 1 over L, the integration.
Why?
Where exactly, Doctor?
DIL over DT.
Or mu can multiply by R. Yeah.
No. It is L di dt.
Yes. Yeah, sorry. Yeah, you're, yes, after voltage.
L minus VC equal to 0. Do you agree? KVL in this loop.
Yes, you're right.
So let me solve now for DIL. So DIL dt equal to minus R over L IL plus 1 over L VC. So I have now a second differential equation. Let me put them in a matrix format, or if I want to put it in the X, okay, let me use the terminology of X, X1. So I need X1 and X2. By the way, okay, what's the output? What's Y will be? What's Y will be? Or V out, sorry. What's V out equal to?
It's IL في R.
RIL. So this is what we have. Now let me assume, okay, X1 equal to VC, X2 equal to IL. And this is basically the same equation which I put in this format. Let me put them in a matrix format. And rather than you can dx dt, let me use x dot. Say x1 dot, x2 dot equal to u. So what will be the matrix in here? What's the first element?
Minus 1 over C.
This is multiplying x2. So the first element will be 0.
0.
Yeah.
Minus 1 over C.
And there will we have 1 over C.
Over C. And what do we have here?
1 over
1
L.
over L.
1 over L.
Minus R over L.
And
0.
Yes.
What is Y? The output. The output equal to, again, x1, x2. So what do we have?
We have 0 R.
R. If you compare them, so x dot equal AX plus BU y equal to cx plus du. So A will be, this is A, this is B, this is C, and D will be 0. So now my system, as I said, I have two first order differential equations. Okay. Now
you can find the homogeneous solution, right, Doctor? For the x dot equal ax plus bu, we can solve it.
Well, we will come to the solution for this system. Okay, we will come to the solution for this system. But now let me focus on the modeling. Now tell me, what will happen if I assume x1 equal to IL and x2 equal to VC? Can I do that?
You just flip the two.
Exactly. If I flip the two, do I get the same matrices?
Of course.
Of course. Of course.
Because x1 and x2, you define them, Doctor.
Yes, but not the same matrices.
But
okay, change them. Okay, let's do x1 and x2 as I said. Okay.
A will be different, of course.
Unfortunately, I think, look, no, the matrices which you are going to get is going to be a little bit different. The state variable,
it will be the transpose, Doctor.
Not unique. But if you are looking from the input from U to Y, the response will be the same. Because basically, inside your circuit, you are just relabeling. But if you are interested between the input and the output, you don't change anything. You change them internally. So the state variable model, what I'm trying to say in here, the state variable model is not unique model. This is which we are going to see a lot, okay, when we have the relation between transfer function and state space. But let me stop in here. Is there any question before we stop?
We want to solve the system.
Okay.
We want to solve the system.
الحين
تشويق للكلاس الجاي.
No, we'll come to it. يجيك الحل ان شاء الله بالمحاضره الجايه. بس الحين this is the modeling. We are at the modeling of the state space system. Okay?
But can you give us, Doctor, idea how to solve it? Because what I'm thinking of
well, simply use Laplace transform.
Laplace transform.
Yes. But we will give you the solution for it anyway. But that's, in that direction you can go.
What I'm thinking of, since we have a first order differential equation, we can, for the homogeneous, it's easy. It will be e to the power the matrix. Exactly. And there is we will use the singular value decomposition for the matrix to find because at the end of the day the exponent in the E will be a matrix. It will not be and this matrix, characteristic matrix, will have the eigenvalues, will possess the eigenvalues. I think there is way in MATLAB because I did that before, but I forgot. So
MATLAB can handle anything. But what you said, there are methods of finding e to the 80 when A is a matrix. We'll come to it also.
Yes, the singular value decomposition.
No, not the singular. The singular, no, you use the eigenvalues, not the singular value, the eigenvalues. Together.
Eigenvalue decomposition, yeah, eigenvalue decomposition, yes. Yes.
There is singular value decomposition, yes. But what we will be using, we're using the eigenvalue.
Which is the V capital lambda V طبعا eigenvector capital lambda V inverse, yeah.
That's correct.
Yeah, this is interesting. So.
It is.